Ok. Allora, ci siamo. Potete fare un comodo una sedia. Ok. Hi, everybody. Sorry for the technical problems.
Okay, you could rest a bit, right? So today we will start with Professor Perton class. His class will be mainly on machine learning, so machine learning, neural networks, and geometric learning for mathematicians. But I'm not sure it will be with those statisticians, right? And some economists
Sure.
with some
Well,
basic in statistics. Let's hope. And Professor Pertoni, he is in Pescara University, in Pescara. So I think that's all. Of course, as usual, if you would like to have the exam with Professor Perton, then tell him not today if you're not sure, but in 2-3 days before he ends the class, okay? So enjoy.
Okay, thank you, Simone. Thank you, everybody, for being here. So, I am a mathematician, and I practice machine learning since 2016. So I know both worlds. And my main objective in these 6 hours that we will stay together is that you understand how many possibilities there are for mathematicians, I mean, for doing research for mathematicians in this topic, which is machine learning, okay? In order to do so, I will try to introduce you to very basic things of what is machine learning and what is the main tool which is used today in machine learning, which are these famous neural networks. This will be a very basic introduction. As you can imagine, you cannot become expert in machine learning or neural networks or whatever in just 6 hours, okay? So I will just try to give you the idea. And as long as you finish this course, knowing at least nothing of this, but just with the idea that the topic is fascinating, I will be happy. Okay, is that clear? So first thing, the topic and the aim of the course. Second, please ask questions. There are no stupid questions except one, the one question which is not asked. Okay, somebody told something like that someday. Okay, so the structure of my lecture is, I would say, unconventional. I will not give you one single PDF with my slides, and I will more give you a reading list in order to teach you how to fish instead of giving you the fish. Another metaphor, very well known. So this is a tentative program, and this is what we are supposed to do today. As I told you, it is not really important to go over everything here. Okay, so please don't be shy in interrupting me if you don't understand something. Okay, so I will give whatever you are looking here. I already have a folder which is called share, which is, as you can guess, for sharing with you. So you will have access to all this material. As you can see, this is a reading list in the sense that, for instance, the first item is, what does it mean learning for a machine? Since we are mathematicians, I assume not every of you do really know what it does mean to learn for a machine, okay? And the topic we are now learning is machine learning. A lot of learning in the sentence. So you see, there are some keywords. at the end of the next 15 minutes, you should be able to understand all these keywords. And there is this font, 01learning.pdf. This means that in the folder share, there is a file called in that name, 01learning.pdf, that I will now open, okay? And next, you can guess there will be something about neural networks, which you can see is just over there. This folder will be shared with you. So let's start. And I open with the application that allows me to write onto it. And these are classical slides, actually. So we start, I can maximize it in a standard way. Like this. Okay. So what is learning in machine learning? First note, if you already know what does it mean machine learning, these slides are going to be completely trivial, okay? So forgive me, but we are just leveraging all the notes we know. So I will start with a very basic problem, which is called regression. If you have never done something called linear regression, this is that regression. Regression in mathematical language means we want to learn a function, as opposite to we want to learn a probability distribution or a classification problem. So I will formulate this problem in this way. There is a function which we call f star. Star in machine learning always often means something optimal, something that we are looking for, okay? Start becoming used to the notation. So there is this f star, okay? We want to know this f star because this f star is solving a problem, okay? Don't forget the empirical component of this topic. This f star, if we know it, we can drive a car. Not us. The function is a main component in driving autonomously a car, okay? This function is the function recognizing cat and dogs in images, okay? So this is a real function. Second, you will never be able to know exactly this function. Forget it, except for toy problems, okay? But it doesn't matter because this function is solving a problem. As long as the function you learn is solving that problem, that's fine for us, okay? Of course, we can assume that if we know a function which is as close as possible to this f star, this is much better than learning a function which is quite far from this f star. Third point, we live in a finite world, unfortunately. So we have a finite amount of data. In particular, we know this f star only in a finite set of points. And this is called the data. The function f star is what we will call the task, the problem we are trying to solve. Okay? So the main question in the slides is, what is the best we can do to find this f star? This is the only things we have, and this is what we aim for. So, first, let's plot the points. So assume these are the points for which we have the value of our f star. You can notice they are in a cloud. So another thing that always happens in this kind of problems, so when I told you we know f star, very often, not always, but very often, we know f star in a noisy way. We know f star, but we are not sure that is exactly the value, okay? This means, for instance, that on the same vertical line, we can have two different values, okay? And in the caption, there is this magical word, which means that these points are not the exact values, okay? But I'm pretty sure if I ask you, a conjecture of the f star of the function, what it is, this function, you will probably tell me something like this. Okay, so let's check. I plotted here two curves, one red, let's say 1, and one should be green, let's say 2. If I ask you which one of these is closer to f star, what would you answer? Number 1. Nobody number 2? Nobody wants to give a third answer? Okay, this is easy. Okay, let's say you're right. And now, still maybe the red one, but you see now the answer is less clear. And actually, I was doing this picture with TIGS, which is very hard to use. I was trying to draw a blue line, which is actually not clearly better than the red one. I didn't succeed, apparently, but if I do something like this, I mean, is this new red line worse or better? Not clear, okay? So we need a definition of worse or better, something that we can measure, something which can be quantified, okay? How would you measure this thing? This is something called the loss. I have these points. These black points are the points where the curve is supposed to pass through. How can you measure which between these three curves is better? With a number. A number that if it is 5 is worse than 3, which is worse than 1.
The distance between the actual value and the value on the red line.
Exactly. Let's say something like this. With this horrendous picture, what do I mean? I mean, for instance, this is the point of the red curve, but this is the real value. And you see the red segment here is measuring the error on that point of our curve, okay? So I measure this error for all the points in my data sets. And I sum those errors. And since we are mathematicians and we don't like absolute values, we prefer the square of the absolute value because it's smooth. And we will have to do a lot of derivatives. We do this summation. Okay, so this horrible formula is just telling you I'm taking the distance on the points I know the value for with the estimate of the value of that point according to my curve. And you notice, very important, I'm not using every point in the data set, okay? Believe me, for the moment, it will be very useful, okay? But for the moment, just forget this detail. Just assume that you are working only with a part of the points. Instead of all the data, we are using something that we are calling training set. Training for training, okay? Because we want actually to learn this curve. For the moment, we are only concerned with how to tell whether this curve is worse or better than another one, okay? So in mathematical language, this is an sort of a finite approximation of a small L2 norm, okay? And this is an approximation of what it would be the L2 norm in the function space between the true function f star and the estimate we are visualizing here, okay? And we are averaging with the cardinality of the data, just to have commensurable numbers. Is this clear up to now? Okay. So the problem is solved. I have a quantity, this quantity, called total loss on the training set. This total loss depends on the function, okay? So if I can solve the problem finding the function which makes as small as possible this loss, I'm done. Can you solve this problem? You can very easily. I mean, find the function, one function that makes this sum the smallest one. Interpolating every point. You can just do this interpolation. The other points, I'm not using them because I'm taking them out, okay? I'm learning only on the training set. But this function has loss equal to 0. And there are many other such functions. Would you say that this function is solving your problem? Remember, the problem was not finding function with 0 loss. The problem was finding function that is likely going to be close in a certain sense to f star. No, probably no. Okay, so first thing, very important. Learning is not feasible. This is bold-faced. It means that is a technical word. Learning is not feasible without hypothesis on the function set, in this case, or on the task we are learning, okay? You can't learn, there is something called no free lunch theorem in machine learning statistics. This is, in some sense, a version of that. You cannot have something which is universal, which can solve every problem, okay? If I can look for every function, I cannot say every function is not meaning. Every function is too big, okay? I have to reduce the function space. So, another technical word, we need to restrict our attention to a model. A model means a family of functions called mathcal f this way, which is a subset of much smaller dimension subset usually of functions. Okay, now the problem is the same, okay, but I have to choose the function not between every function, but just in the function I have chosen as a model, okay? And now maybe the interpolating function, the piecewise linear function, is not in that set, okay? So this is sometimes solving that problem because I don't want that function, probably. And just for the sake of clarity, simplicity, here and hereafter, we are assuming that this model contains functions which are parametric functions, meaning they are associated to a parameter, okay? This is a parametric model, meaning that now I can identify functions with vectors with a certain dimension, Rd, okay? And I say this is for the sake of simplicity, because in machine learning, you also have non-parametric models, okay? There are several of them. You have probably heard about decision tree or random forest. These are the classical example, or K nearest neighborhood, maybe if you are. These are the three main non-parametric methods in machine learning. We are not interested, actually, we are interested, but we have no time to be interested here on this. So starting from now, we have functions identified by a vector of dimension d, okay, a parameter. Now, given two functions, that is, two vectors, can we say which one is better? Well, now we can do the same. Formally, this is the same, but now first it depends on theta, this loss. And now the function, maybe it cannot be the function interpolating points. But of course, this depends on the model. The model could still contain the function interpolating points. So, what I want to say is that, again, if I obtain a very small loss, okay, maybe the model is not containing the function interpolating points exactly, but maybe it contains a function like this that maybe makes something like this, which is almost passing through the points. Okay, so the error is not 0. The error is something bigger than 0. But again, this function is not something that is probably going to solve the problem. Okay, so at the end of the day, we have still this problem. How can we solve this problem? We need a way to quantify this statement. This function is almost interpolating, or this function is almost very close to f star. I want the second one, not the first one. Okay, how can we measure this in some way? We need new data, right? To do what?
See how the function new data.
Very good. You already knew that. Or you're guessing, or you already knew that. Okay, thank you anyway. Remember that we left points out of this argument. Now it is time to use them. Because if I now take this function and I measure the error, this quantity, but not on these points where the error is of course small because I have picked up the function which makes this error small. If now I take this function, I don't choose another function anymore, and I measure the error on the other points, what would you expect to happen? If this function is bad, then that would be probably shown up. Okay, so I measure the loss not anymore on T, the training set, but on the set that we called S, which is the test set, test for testing the solution. Okay, and now I measure. Let's say that the loss of the function on the training set was 0.2. And let's say this loss is now 20. Would you say that your model is good? No, because they are too different. Okay. What if the loss is 0.3? Of course, you expect the loss on the test set being bigger than the loss on the training set, where you have minimized something. In that case, 0.2, 0.3, you would say, okay, this is good enough. Okay, in this case, we say that the solution you have found, the function you are considering, is generalizing well to other data points. Of course, you have no guarantee that this is close to the true function, but we have finite data. I mean, this is almost the best we can do. Okay. Now, there are two components in this in this argument that plays a big and important role. Something called bias and something called variance. They are related to bias and variance, of course, in the statistical and probabilistic meaning. But just to understand the big picture, it is clear that if the model F contains a lot of functions, in particular, if it contains the interpolated function, in that case, I can find loss 0. So bigger the model, where it is not clear what bigger means. There are several notions of dimensions. If you heard about the VC dimension, this is the most famous dimension for the capacity of the model. But anyway, the bigger the model, the more function it contains, more likely you are going to find a function which is almost overfitting. Okay, which is probably not good. But the bigger the model, sorry, I was going to say another thing. The bigger the model, the best you can hope to have a function which is approximating the true function. Okay, so this is the small bias. But you have also an algorithm that is using the data you have to find the approximation, okay? And depending on the data and depending on the algorithm, you can find a good approximation or not a good approximation. And more function in the set, if you fix the data, more function in the set means more likely small bias, because more likely you can approximate F star quite well. But less likely is your algorithm going to work with a fixed amount of data, because you have more functions in which to pick up the solution, just trivially, okay? And this is what is known, this is an instance, an explanation of what is known as bias variance trade-off. In machine learning, quite often, you have to choose the right trade-off between a model which is powerful, but not too much powerful, capable, but not too much capable, and an amount of data which is good for that model. Okay, in machine learning, you should always match the capacity of the model with the amount of data and not with the complexity of the function that you are looking for. Okay? Trivially, this means that if you have 10 points, you should never use 1 million of parameters, because of course, with 1 million of parameters, maybe just think about the polynomial function up to degree 1 million. If you have 10 points, 100 points, 1,000 points, you always can interpolate, okay? As a rule of thumb, you should use 10 times the number of parameters than the number of points you have to train, okay? This is the classical machine learning rule of thumb. Spoiler, today, neural networks uses tens or hundreds of billions of parameters, while the data points are millions, 10 millions, 100 millions, but several magnitude orders lower than the data points. So this, which is almost an axiom, a standard paradigm in machine learning, today is not anymore true. I mean, neural networks are such models with such a huge number of parameters. They work very well. Do you know why? I don't think so, because I don't know neither. Nobody knows. So this is the first research point that you can put on your diary, or research points that I will suggest to you for you as a mathematician in data analysis. Okay, this is one of the biggest questions. There are, of course, several research lines, very promising, several explanations supported by empirical and theoretical facts. When I say theoretical facts quoted, I often means that are supported on toy problems. Get a neural network with one layer, okay, or do this kind of problem which is built just to make that theoretical argument work, okay? But anyway, this is a very fascinating research topic.
Okay. Sorry.
Yes.
I still don't understand why not choose immediately D equals T. Is it just a computational problem? Why not immediately try to
train
data simultaneously?
And after that, you need the test set. Okay, you use all the data and you find this function. Now the question is the
optimize all the data you have?
Yes, but the original problem was not find the best approximation on your data. Let's say D here instead of T. The original problem is finding your approximation to the true function, also on points that you don't have the value for, okay? So how can you now quantify? Okay, you have found this function, okay? And on this point, I agree that on this point, this function is very likely going to be Now, how can you say whether this function, when we are, for instance, extrapolating, well, when we are here, this function maybe will go here, how can you say whether this value here is a good approximation or it is here?
Comparing T and S inside B will have the same differential. Will not tell me what happens over there.
But, okay, because we are thinking in a deterministic way. Okay, deterministically, also when we have the generalization on the test set, we cannot say that this is not going to happen. Is this possible? Yes. Also, in the case of good generalization, very, very good point, you're right. So the differences between this setting, the differences between the possible and probable. Is this going to happen? Is this possible? And this is something I don't want. Of course, this will always be possible. But what is the likelihood? What is the probability that this is going to happen? Now we can use probability. And if we have several points that we have used for test, more, at least in a qualitative way, do you agree that if I have 1 million points that I didn't optimize the function for, but now ex post, I'm checking my function and I see that on the first 10 points is very good, on the first 20 points is very good, on the first 100 points is very good. What is the likelihood that this is going to happen just because chance? I mean, if it happens on 1 point, okay. 10 points, 100 points, 1,000 points. Now I'm testing on 1 million points. And that function that was never trained on those points, which are random for that function, okay, because the training algorithm have never seen that, on those points, there is a good approximation. Would you agree that now, when I ask you, is this possible? You still answer, yes, of course, and this is the problem of the finite data. The only way to ensure that this is not possible is to have the true function. So, yes, it is possible. It is probable. Do you say probable in English? Oh, sure, okay. I would say it can happen, of course. Possible means probability higher than 0, but I would say with with low probability. Can we quantify this number? Yes, this is called likelihood in statistics, in probability. I can quantify in a very precise way what is the probability that, given a certain delta, something, how are they called, the Chebyshev inequalities, some probability that the distance between this f with f star is greater than epsilon, greater than delta, sorry. Is this? Should be minus 1 minus delta. I'm not sure. I mean, this kind of inequalities. Okay, there are this kind of inequalities that you can write that can tell you, and this number here, you have numbers depending on the number of points you tested your function for. Okay, this is the setting that you use in statistical learning to do this sort of estimates, and in this number, there is what I was telling you before, this VC dimension, which is a dimension quantifying in some way how big is your model, how many functions are in your model. Okay, so yes, this is all, you're right, this is always possible. But if I take out a lot of points, then I can tell that with high likelihood, this is close to the true function. There will never be the certain answer in this setting. Okay, you know, in this kind of discipline or topic, you do statements which are called PAC, probably approximately correct. Okay, that means you never have correct. You always have something which is approximate correct, but you can never be sure that you have approximately correct answer neither, because you always have finite amount of data. So the only thing you can have is having a statement, a mathematical theorem, which is probably with a certain probability that you can quantify in terms of epsilon and delta, approximately correct. Okay. So I was telling you about the regression problem, which is learning a function, a numerical function. Okay. What if I want to distinguish between cats and dogs? This is not a function. I should have a function giving you cat or dog. Well, we formalize it this way. I will learn a function into Rm, where m is the number of categories. So cat and dogs, 2 categories. I will learn a function in R2. Actually, the image of this function are probability distribution, meaning that I don't have every point in R2, just a point in a simplex, meaning 2 numbers, positive, which sums to 1. Okay? And they are giving me the probability that that image, which is the input, okay, is a cat or a dog. Of course, I could have images which are not clearly cat or a dog, and maybe they will give me 0.6, 0.4, saying, I think 60% a cat, 40% a dog. If you think this is not a true answer, and if you think that you are always able, looking at the picture, to say clearly if it is a cat or a dog, this is not true. I could show you pictures of animals. I tell you this is a cat or a dog, but you are not able to say because they are very similar if you are not an expert of that topic. Okay, so I'm saying that having a probabilistic model giving you, instead of true answer, giving you probability as an answer, this is also very, very common and very real life situation. And now the loss you minimize usually is what is called the likelihood. Meaning, if I have in my training data, I have given to you this kind of examples, and these are cats, these are dogs. Giving these examples, what is, in your opinion, the likelihood that this new image is a cat? What is the likelihood that this new image is a dog? Okay, and I want to maximize the likelihood that a cat is a cat and the dog is a dog. And if you put the minus in front of that, you want to minimize it. In machine learning, we usually minimize. So when we have something which should be maximized, we put the minus sign in front of it. Okay, but just the loss changes. Everything else is as before. Okay, other questions? I hope this is because it is clear and not because I'm boring you. Okay, so this is a recap. Just go very, very fast. Oh, okay, I promised you I would tell you what is learning. Up to this moment, I told you what is the problem. The problem is to find a good approximation, a probably good approximation of a function f star. What does it mean learning? Well, you will see that usually we don't find this approximation with one single formula, a closed formula, except for linear regression with L2 loss. There is a closed formula. You say, okay, this is the best approximation I can have in my linear model. But usually, in order to find this minimum, you have to find the minimum of a very high dimensional non-convex function. So first, forget the global minimum. You just find a local minimum and you cross your finger that it is going to drive your car without crashing. And second, you find it with iterative numerical methods. Okay, so you have steps in which you have a parameter, you have this function, you say, okay, I think this function is a good approximation, but not so good. I do a step of my algorithm that is going to minimize the loss. You find another function corresponding to another parameter, theta2, which is likely going to have smaller loss, okay? And so you say, okay, I'm learning because the loss from year to year is decreasing, okay? And of course, you should always consider the test loss. As soon as the test loss is going to increase, then you should be aware that maybe you are not anymore learning, but you are entering the realm of overfitting, okay? And then you should maybe stop, depending on which algorithm you are using. Again, the algorithm we are using is always gradient descent, just to clear. There are several optimization algorithms, but the most used with neural networks as of today is the gradient descent. So I will talk a little bit more of that later. Okay. And I want to point out that in any case, at the end, if you want to really be sure that your problem is solved, so that you have a good F-star approximation, you can just try your solution on the field, on the real problem. Is this going to be easy? Sometimes, very easy. For instance, if you just made a software that plays Go, you just organize a match against the world champion of Go, offer him $1 million if he's going to win, he's going to accept, of course. Otherwise, you offer him $10 million, and eventually he will go in that, and then you play game. You're not harming anybody. You're making a big show. Everybody is very happy. It's a win-win. Or your problem was to produce a completely automatic heart implants procedure. Now you want to test on the real patient. You offer him $1 million, $10 million. I wouldn't accept. I don't know you, but neither I would accept eventually. I mean, because I don't want to be tested on something that, okay, on a lot of training points, the loss is 0. On the test set, a very big test set, the loss is almost 0. So I'm pretty sure, I'm pretty confident that this is going to work. 99%, this is close to F-star. I wouldn't like to be the one testing whether that 1% is occurring just in my case or not. So if you can test your function, the real problem, just do it. And this is the best way to be sure that your problem is solved. Again, just in the likely term, because you cannot be sure that there is not an instance on that problem where your algorithm will fail. Also, AlphaGo, the algorithm playing Go as a superhuman, has some flaw that can be exploited, and recently they have been exploited in a very clever way by another machine learning algorithm, by the way. And so there are situations that are probably never going to happen in a real game, but there are situations where that software is not so strong in the game of Go, okay? So you will never have the exact solution. I think, okay. first point, first check. Now let's go back to the outline. Yes?
What is that probability referring to? Like the noise do you make assumptions from the noise, or are you saying from any noise that you can come up with, this probability is going to be?
If you want to make a formal statement, you have probably to make assumption on the noise. In the statistical learning instance I'm referring to, I don't think you're assumption of the noise. You're just saying the probability that the function you are considering, you are picking up from your set, is close to the function you are approximating. Yes, I think so. But in certain situations, you of course make assumption on the noise. For instance, it is very classical in the linear regression. Depending on how it is taught to you, the linear regression is always assuming, explicitly said or not explicitly said, that the noise is just a random noise, white noise, normally distributed. This is the classical assumption you make. Also, in very recent, very successful models, the models that generate images that you have heard about DALL-E or the website "This person does not exist" or something like this. The models behind them are generative models that can create images, and they are based on diffusion processes, which is something where you add some normally distributed noise to the original image, and then you reverse the process. I'm not sure, is this answering more or less your question?
For F star, one doesn't make any assumption.
If you want to make theorems, you have to make assumptions. This is the no-free lunch theorem, and what I was telling you before. Sometimes, this is also a very good question, thank you. Sometimes these kind of assumptions are very natural. Maybe, if you want to recognize whether a picture contains a cut, the same cut, the same pixel by pixel cut can stay here or here or here or here, also slightly rotated. You would always say, yes, there is a cut, right? Can you recognize some invariance? Can you say that your F star that you are trying to learn is rigid in some sense, because it is invariant by the action of rigid movements, at least. And I must say, you can also slightly expand on contract the image, isotropically maybe, and you obtain still a cut. So it is invariant also for a bigger group than isometries, okay? So in that case, assuming that your F star is invariant for, which is a very strong assumption, would be true, okay? In other cases, this is not clear, because, for instance, in medical images, there are some assumptions you can do, some more assumptions you can do, but just because of human expertise, because the human experts in that kind of illness, they are telling you, yes, usually I think this property holds. Then you can risk the correctness of your model, assuming the more the assumption you make on the model, of course, the easier is the problem. The trivial case being you make so many assumptions on F star that you know F star, because it is uniquely determined by those assumptions, okay? And yes, this is a problem for us mathematicians. We need to make assumptions to make theorems, okay? But as soon as you enter the realm of the probably and approximately, then things becomes easier from this point of view. You can relax the assumption. By the way, making the assumption that your problem is invariant or equivariant under the action of a certain group is the basis for geometric deep learning. Geometric deep learning is exactly the part of machine learning studying what to do to build models which are very efficient and which break the bias variance trade-off when you can make this kind of assumption. That I already spoiled you, the fact that for image recognition, this kind of assumption is not only reasonable, but let's say true. Okay? Other questions? Yes?
One related question. So, how many data do you need to collect in order to obtain a reliable function? I mean, is there any estimate to quantitative estimates?
More points, the better. As many points as you can have is better, of course, because we are working with probabilities. So if you can test your function on more points, if you can learn your function on more points, you are going to obtain something better. Of course, the answer depends strongly on the task and on the model you want to use, the algorithm, optimization algorithm you are going to use. With the same amount of data, of course, you can have good results or bad results if you use good algorithms or bad algorithms. With the same amount of data, you can have good results or bad results if the problem is very complex or very easy, and so on. The threshold is one. There is something called few-shot learning, which are techniques used to learn from one data point. Sounds crazy, right? But if you had just one data point and you want to cure cancer with one data point, you do what you can do. Of course, would be much better to have thousands of images, millions of images. In medical applications, I have never seen more than 1,000 images. 1,000 images in a medical application are considered big data. I recently won a PRIN with a doctor, and we are starting a project on bone cancer. And he's working on this field since more than 10 years, 20 years. And he told me before the application that I would have had all data available to me, as much as I want. I asked how many. Oh, I can give you also 100 pictures of this kind of cancer, which is very rare, by the way. So 100 pictures, it is actually a big number, but not for the techniques I was planning to use. So I will have to use techniques designed explicitly for few data points. You are welcome. Thank you. To you.
Like computational costs in using huge data set?
If the data set is big, you mean if there are computational costs? Yes, of course. It's always a matter of trade-off. Yes, yes. Life is not easy in machine learning. Every application is a single instance of a problem. But as long as you learn general techniques, you have a big bag in which you can pick up techniques, choices, and so on. Also, the splitting of the data set between training and test. How much? 50-50? Usually you reserve more for the training than for the test. I would tell you 80-20, but 85-15 is going to work as well, probably. Maybe 70-30 is going to work better. Maybe you can do, if the experiment is not very long time, it takes not a long time, you can try the same algorithm, but with different splittings of the data set, 60-40, 70-30, 80-20. And then you choose the model which is performing better, where better means in terms of generalization and loss and so on.
Would it be correct to say something like smaller is the test, higher is the probability to have some good distribution of the data, something like
good distribution of the data or good solution?
Distribution of the data, so that the function you choose is probably indeed smooth and
the distribution of the data is again another dimension that somebody you try to learn the distribution of the data. No, it was okay. Distribution of the data is one thing. The function usually the function you are trying to learn is the mean of this distribution and something like this. Okay. And well, if you have for what we said, if you have very small loss on the test set, this is going to be a good thing. If you are sure that this is not interpolating points on the test set, because sometimes this can happen. For instance, think the situation in which you choose your points, you think wisely, and you divide the points 80-20, but you don't realize that you have chosen for some reason these 20% points in the test set, you have chosen duplicates of points in the training set, because there are correlations in the procedure for picking up the points, the data points. Of course, you will have very small loss on the test set. You will be very happy. My model is working. No, you're just interpolating on the training set, and since those points are in the training set, you obtain zero loss over there. So how to pick up the point for the data set is another big problem. And if you want to make theorem again, you can make probabilistic assumptions on the distribution of the data points. So, now, I told you we are using parametric models, okay? Parametric models, there are a lot of parametric models. We are interested in a certain family, those models called neural networks. 90% of the hype you see as of today in the newspaper, ChatGPT and so on, all this success, I would say 99%, not just 90, are due to this family of models, okay, to neural networks. ChatGPT, for instance, is a neural network with 5 billions of parameters. Billions, not millions, billions, okay, milliardi. And it is not the bigger one. The biggest model, as far as I remember, is still some large language model with, I think, 400 or 500 of billions of parameters. So if you are a statistician and you are used to think to 100 parameters as too many parameters, this is a completely new world with completely new problems. Okay, I'm telling you this because you could be tempted once you see something called statistical learning, which is something I suggest you to study. You could be tempted to say, okay, this part of machine learning is just, I already know this kind of things, it's just statistics. Okay, in a certain sense, you're right, but the high dimension of several components of this topic makes the problem a completely new problem. Okay, I will be back on this later. So, neural networks, share, neural network, open with. Now I'm trying to tell you what is a neural network. Are you happy? I hope so, because they are very cool objects. And have you ever thought about the fact that there are several different ways of describing a function? We, as a mathematician, we are almost used to say a function is f of x equal to some closed formula. Or let's say some closed formula given in this way, some formula here, some formula here, defined in two pieces. Okay. But if you remember, when we were much younger than today, the first function that were defined to us was something like this: x, y, 1, 1, 2, 4, 3, 9 dots. Okay, to define the x goes to x squared function. This is just another way of describing a function. And I'm pretty sure you know another way, that is this one, called the graph of a function. Okay, so there are so many ways to describe a function, and I want to give you a fourth one. This way is called computational graph, and it is what you're looking at. What is a computational graph? Well, it's an alternative way of describing a function. This computational graph is describing this function. Okay, in which way? I will tell you now what I mean with this picture. Okay, first, you can notice the arrows. So we are going in this direction. Okay, here there is the input, and from here you can see there are two inputs. So the function, the domain is R squared, or a subset of R squared. Okay, then there are arrows with numbers on the arrows. For instance, here there is a -4. By convention, we are agreeing on a notation. This means that the quantity from here connected by the arrow is multiplied by -4. Okay, so this quantity is multiplied by +3. And then another convention, when two arrows enter the same node, this is a graph, we sum those values. So in this node, by convention, there will enter the value -4x1 plus 3x2. Is this clear up to now? It's just a Sudoku again. And now another convention, when there is something written inside, there will always be or will be implicitly assumed, you apply that function to the quantity entering that node. So here there is the exponential function, and so this becomes e to the power of this. Okay? If you do the same here, you sum x1 minus x2, and you elevate to the power of 2. Okay? And you can say, and another convention, if there is a small number here, this is called the bias. This is an affine translation, meaning that you will just put the number as a known term at the end. So, for instance, here we will have 1x1 minus 1x2 plus -2, all of this squared. Okay? And you can just recognize two pieces of this function. Now, again, all these quantities, the first is multiplied by 1, so it's not multiplied. The second one is multiplied by 3. And at the end, when they enter inside, they are summed. So you obtain this sum. And there is a bias here, +5. So you add 5. And you apply the function inside the node, called activation function, which is, in this case, is the identity function. And so don't do anything else. Do you agree that with this game, we are describing, I admit, in a apparently more complex way, we are describing a very nice function that can be easily described by a closed formula. Okay. Okay, so the terms activation function inside the nodes, weights these numbers, bias these numbers. Layer, this is the first layer. Actually, this part is the first layer. This is the second layer. So this is a computational graph described by 2 layers. The input layer has 2 input nodes. The output layer has 1 output node, meaning that the function is from R2 to R. Okay? Now, we are interested not in functions, but in parametric function. So allow me to put parameters instead of numbers. If I do this, now I'm describing this function, which is actually not one function, is a family of functions, okay, given by parameters. And you can see that this kind of structure is called computational graph, is very good in describing hierarchically. Do you say hierarchically? Hierarchically, thank you. Defined functions. So this is a function defined by what? By decomposition of 2 functions. First, you apply this sigma, whatever it is, and then you apply this other activation function, in this case, just the identity. This is still not very good looking, okay? But now you can also admit that this is also not very good looking. Can you imagine a better way to describe this? Here I'm multiplying by numbers and then I am adding a number. This sounds like a linear and a fine operation. So maybe I can just use matrices. We are mathematicians, so we like matrices. So this function is described by this computational graph. Now things sounds easier. I mean, I'm not any more sure that this is better than this. Okay? Now imagine I do the same, but not with 2 layers, but with 10 layers. I can easily describe this picture with the same picture just by cutting here and putting dots, saying everything is just like this. If I want to write the closed formula for this, I need to put here sigma of sigma of sigma of sigma of sigma of 10 times. Of course, also here I could say in some natural language that I am composing the same thing 10 times. Okay, but this picture is now at least the same level of complexity as the closed formula. Okay, congratulations, you will learn what is a neural network. This is a neural network. Okay, so a neural network is just a particular model, in the sense I was describing to you before, that is a parametric family of functions where the parameters act in some sense linearly in this family, but are composed hierarchically in a non-trivial way by activation functions. And from here, you understand that clearly the activation function shouldn't be linear. Otherwise, you are composing linear functions, and at the end, you obtain a linear function. Okay? But this is also a research topic. In some sense, that I will not touch and just mentioning, neural networks where the activations are linear are interesting because the kind of hierarchy you give to that linear function by the decomposition in layers, also if you obtain the same function at the end of the day, but you give that different hierarchies, this could strongly affect the learning algorithm. So the learning algorithm will learn different things. And so this is also a fascinating point of view for a mathematician, because at the end of the day, the function, the global function, the parametric function given by this big computational graph is the same, but behaves differently. Okay. Just to understand how this works, this is a function from R4 to R3, described by how many layers? Tell me. First line. Good.
So it's the input layer, the first one, that's one we circle.
Okay, so this is one layer.
Yeah, then there is one, two, four, five, we hit on mouse.
So total number of layers.
And there is also the condition.
Okay, the output is this one.
Seven.
So I would say 6. 1, 2, 3, 4, 5, 6. But there is a sort of ambiguity in this language. One could think of layer as the layer of nodes. In this case, 7 would be the correct answer. 1, 2, 3, 4, 5, 6, 7. And of course, in this case, the first layer is the layer of the input nodes. The last layer is the layer of the output nodes. I really invite you not to do this. I invite you to think of the layers as the functions that are composing the computational graph. So this is why I'm telling you this is the layer and not this and this. Of course, this means that the input layer is not the set of nodes, but is this function. And the output layer is this function. And this gives the internal layers an important, a diverse role. And they are called, for this reason, hidden layers. So in this case, I would have one input layer, one output layer, and 4 hidden layers. Okay? When the neural network has several hidden layers, the neural network is called deep, as in not shallow. How much is several? 3. Sometimes also 2. This is for historical reason, up to 2006, so less than, let's say, 20 years ago, the neural networks were not able to learn these parametric functions, which are this model. If you try to learn a problem, a non-trivial problem, with one neural network with 3 hidden layers, or 4, that would be science fiction, the network was not going to work. The loss was not decreasing, okay, due to several reasons. The main one is called vanishing gradient. But, and so they were saying, okay, a neural network is deep if we have more than 2 or 3 hidden layers. If nowadays, starting from 2006, there has been developed some mathematical trick, some theory, some
theoretical problem, non computation.
Theoretical, yes. Well, computational in the sense that at certain point the machine numbers becomes close to 0, and you can't escape this fake minimum in some sense. Also computational, not in the sense of computational power, but computational in the sense of numerical analysis. But anyway, now these kind of problems are solved in the sense that we can learn with very deep neural networks. I remember reading a paper, a proof of concept, where they successfully trained a 1001 layers neural network. That is absolutely huge. But nowadays, having a neural network with 100 layers is common and very computationally intensive, of course. And okay, if you're working with deep neural networks, and you are working with deep neural networks, you are not doing machine learning, you are doing deep learning. Okay, so you now know what is deep learning. Deep learning is doing machine learning with neural networks, which are or can be deep. Okay, of course, when you start a problem, you will start with a simple neural network, so maybe nothing wrong in trying 2 or 3 layers at the beginning. Okay, sometimes you have a structure on your input, And you can see that kind of picture can become very elaborated, like this one. This is a picture of a neural network which is working on images. And so an image is not just a set of values, which are the pixel values. Okay, let's say a gray image. Every point in the image is a number between 0 and 1, and 0 and 255. But you have also structure. You understand the rectangular structure in the image is very important. If I take the image and I create a vector just by aligning the rows of these values, you're not recognizing the image anymore. Okay, so there are neural networks using this structure, this rectangular or square structure, to learn on images. And these are called convolutional neural networks. And this will be the topic of the next lecture. Abbiamo finito. Accidenti. Okay. Okay, so consider this now, all of this, a reading list with the material that is here. So we are working with neural networks. I will try to just go through these points. So we have this parametric model, okay? And remember, we have data points, training points. We build this loss, okay? Remember, the loss is the summation over the points in the data set, okay? And the summation is made by very simple component. The summation is made by, in the summation over x, y in the training set. If you remember, you have the model, that is the neural network is giving you a function. You have fixed some parameter. You compute the model on your xi. For xi, you have also the true f star. You have the true answer, which is called yi. You do this, and you square, and you make this sum, okay? First, these data points can be millions. So this is a sum of 1 million of data points. Second, this neural network can have 10, 20 layers. So it is computationally expensive, okay? So we have 2 points here that are complex for computations. So forget a closed formula for finding the derivatives of this and solving the system for critical points and then checking which one, as we are used to from the second year of mathematics. Okay, you can't do this. So you use this very nice method you have probably heard about, which is called gradient descent. Gradient descent means just look at the gradient and follow the gradient on the opposite direction because you want to go downhill. Is this clear to everybody? Okay. Well, you could say, okay, but to compute the gradient, I need to compute the derivatives, the partial derivatives. And I told you that computing the derivatives of this function is not feasible. Okay. Well, I meant computing the symbolic derivatives of this function and solving the system with a closed formula for critical points is not amenable. But numerically, if I give you a certain parameter theta, and I ask you to compute the gradient of that function in that point, okay, so not a symbolic gradient, but a vector with numerical components, this is surprisingly quite easy. It's a family of algorithms called algorithm for automatic differentiation that leverage the computational graph structure and the chain rule, of course, to compute the derivative in a very easy and very, very fast way. This algorithm This is a family of algorithms, which are called of automatic differentiation. And okay, how they are used with neural networks is called backpropagation. This should be in boldface because a very strong technical word. So in order to compute the derivatives of a neural network, you use backpropagation, which is an algorithm that if you give a point, a parameter, okay, and you can ask this algorithm to give you the gradient in that point. Now you can do gradient descent. Is this arrow this way? Let's say we are on the parameter space. Is this arrow this way? Then you go in the opposite way. And if you have not made a very big step, likely the function is going down. And then you land in another point. You ask the backpropagation again for the gradient, and you go in the opposite way, and so on. This is the gradient descent method. Theoretically, this method, if you choose wisely these steps you are doing when you move, is converging, of course, to a local minimum, not a global one. You have no guarantees on that unless you have convexity, you don't have, of course, because this function is the composition of several nonlinear functions and so on. And problem solved. Okay, not yet, because I'm solving the complexity given by the computation of the gradient, but I still have to compute the summation over 1 million of training points. At every step, I have to compute the new loss and ask backpropagation to give me the gradient of the summation. And here, probability helps us. Stochasticity helps us. We don't do all this sum. We just choose, let's say, 10 points, 100 points, randomly. We pick up 100 points, and we build a partial loss. We compute the gradient of that partial loss, and we move in the opposite of that direction. If we are choosing the points every time randomly, you will see that for probabilistic reason, or large low numbers and so on, this method will eventually converge to the local minimum. Yes? You compute the whole graph, yes.
All of them, they are PDA.
Yes, yes. Fantastic, right? This is the magic of the backpropagation. Yes, you can compute them in 2 steps, one forward step of the computational graph and then one reverse step of the computational graph. Iteratively, you touch every point, and when you touch a node containing a parameter, that node is augmented with the derivative. And this is also very, very fast. Of course, there is a lot of optimization theory in this kind of algorithms.
Sorry, what about tests? You're also supposed to minimize the loss with the tests.
No, absolutely. You are not supposed to do anything with tests. First rule in machine learning, never touch close S, the test set in a drawer, and throw away the key. This is what you should think about. S is just used at the end to test whether the function we are looking for now, with the gradient descent, at the end of the day, we will have a function. And we will say, okay, I have this function which is solving the problem. I'm curing cancer. Okay, let's see if this function is really curing cancer. How can I say? I have the test point. I try on the test point, and if the loss is not comparable with the loss I obtained on the training set, I throw everything away, I shuffle all the points, I choose a new training set, a new test set, and I repeat from the beginning. Okay, of course, you don't really do this. There is a way, by using a third set called validation set, there is a way to check whether your model is learning but not overfitting on the fly when you're learning, okay? There, of course, there is a lot of things that I'm not telling you, sorry, but this is the general idea. But remember, this is very important. Never, the test set doesn't exist up to the very end, okay? Because if you use that also just to peek at the loss, let me check the loss. Oh, it's working. Then you're conceptually spoiling your recipe. From the statistical point of view, this should never be done. Okay, because at the end you are saying, okay, my loss is small on the test set after you have seen that your loss is small on the test set. Okay, very, very good. Yes, just as you're saying my loss is small on the training set. Of course, I built the function in such a way that was minimizing the quantity.
Test set to be completely randomly, or do you try to get spread of points?
You mean how do you choose training, validation, and test? Usually you try to do that completely random. But as I told you before, this is not really clear how to do this. Also, it depends on whether the data set is balanced or not. Maybe you want to learn cat and dogs, but your data set is only picture of dogs. Good luck with that. Okay. And so I was telling you, you can just choose 10 or 100 points to build the loss, a partial loss, and compute the gradient. How many points do you think is better, 10 or 100 or 1,000 or 7 or 42?
I would say 42, but
Yes,
that's
but for other reasons.
reasons.
Okay, what I want to say, of course, there is not the correct answer. You can choose as you like. This is called the mini batch size. The batch is the whole training set. The mini batch is the part of training items you are choosing. And sometimes you choose one item. So you just pick 1 point and you build the loss on 1 point. That means there is no summation anymore. And you minimize this loss. And this is what is called stochastic gradient descent, okay, or online gradient descent. Okay, here there is the link for the automatic differentiation, stochastic gradient descent done. Okay, and then I will share with you some code. We have no time now to show you the code, but I prepared a notebook with some Python code to let you play with that if you want. If you have nothing to do in the weekend, you can try. I can just maybe show that to you, and then you can start with question. We are over. I'm just showing you the code. So this is a sort of a tutorial of what to do, okay? But just to understand how simple these kind of things are, once you understand this kind of language, this is a framework called Keras, okay? We are writing a neural network, a model, a parametric model, neural network, we know what it is, with something called Keras. And look how simple it is. I'm telling my Keras that the model will be a sequential model. What does it mean? It means that I will define the layers one by one in a sequence. Okay, now I will add layer. I already told you this technical word. So the second line, add 1 layer. Which kind of layer? I haven't told you, but the computational graph you use for neural networks have always the same activation function in the line, the vertical line on nodes, and there are always all the possible connection between the 2 lines on nodes. So I showed you the metrics. Okay, so this kind of layer, there are several others. This kind of layer is called fully connected layer or dense layer. So I'm adding a dense layer. This dense layer, how many input nodes has? Can you tell me how many input nodes has this layer? Input dimension 784. Okay, so this is telling that at the beginning you have not 2 or 3 x, you have 784. This is the dimension of a 28 by 28 pixel image, by the way. This is why it is this dimension. How many nodes in the output? In the first layer? 64. What is the activation function? It's an activation function called ReLU. Doesn't matter what it is. Always use ReLU. Okay. Next layer is simpler because you have only to specify how many output nodes you have. Why we are not specifying how many input nodes in the second layer? Because they are coming sequentially from the previous layer. So input 64, output 64. And at the end, 10 nodes. Why 10? Because in this problem, I'm building a model which is able to recognize by the picture handwritten digits. So it should be able to distinguish between 10 classes from 0 to 9. And so the output will be a probability distribution on 10 classes. So the output will be a vector of 10 numbers summing to 1 and all. Okay. And this is done with an activation function called softmax. Softmax is just taking a vector of 10 numbers and transforming it in 10 numbers in a simplex. Okay, I think we are done. Question, of course, if you want. And just to tell you that next lecture, I think we will do what we have to do. I mean, I will not do the part I skipped because I think I explained very, very quick. Okay, so in the next lecture, we will say something why neural networks are very nice, and in particular, what are convolutional neural networks, the ones used with rectangular images.
I don't remember, but did you mention how the exam works?
How did?
The examination works back at the end of the course.
Oh, no, I didn't, because I have no idea. Usually, if I have free will on this, okay, so usually as whatever you like. Can be a classical exam in which you tell me something about the course, and it can be a project. If you like to make your hand dirty with code, I will be very happy to have some code, some toy problem. You can build a neural network for digits or for other kind of images. If you like the idea, you can read a research paper. This is also a classical exam I like very much. The research paper could be chosen by you and agreed by me, because otherwise you are going to choose something horrible or something very, very difficult to understand. And as long as you understand 5% of that research paper for the exam is fine. And something more? If you have other ideas, I will be happy. So the exam, I mean, the exam, in my opinion, if you follow what I'm saying, should be very easy. Oh my God, these things are so nice. Okay, I must say this reading list I'm giving you is probably, if you want to follow it entirely, it will take you 1 year or more. I mean, this book, Probabilistic Machine Learning, I think these are 2 volumes of 500 pages each, very, very dense, very mathematically dense, but they are really beautiful. And this YouTube course, also a lot of lecture, but the teacher is really fantastic, strongly suggested. But this is topic of the end of the next lecture. So, okay, here we are. Thank you again.